OK, so I'm here to talk about particle physics and accelerating it, to use a pun. OK. So let me begin by setting sort of the context. Particle physics is what I call the most industrial field of academia, sort of this tension between academia and industry. It's sort of in both, because the goals are academic. It's to explore strange new phenomena, seek out new particles and new interactions. But the scale is industrial. So we billion-dollar hardware, planning on decadal timescales, millions of lines of code. It's a big deal. It has to work. It's big data. This summer, CERN just passed a 200 petabyte milestone. But it's not that big. Because, so this is a picture that I show my colleagues when they are thinking that we're sitting on the world's largest data set, as we traditionally have been. That this 200 petabyte milestone, which is the history of particle physics at CERN up to the present, is for some web services 2 trucks. It would be a road trip for them to take it to some data center. But on third hand, it will be getting bigger. So there's this high luminosity LHC project coming up that we all know is coming. This is today. And this is how the data is going to scale. We will be getting into the exabyte range. And we have to somehow figure out how to do that without buying orders of magnitude more computers. That's not on the table. So another aspect of this is that our software developed outside the big data ecosystem. So on the left are all the software tools that we're very familiar with and we work with a lot. And on the right is this big data ecosystem. And I'm including in that scientific Python and the machine learning and stuff, all that. And really, it's not outside, but before. Because all these packages on the left, they have these long histories that go back, some of them into the Fortran era. Most of them are, I don't know if I can say, certainly a lot of them are decades old, and they need to be maintained. But this big data thing happened while we were building our experiment. Actually, let me put in a little bit of context. The experiment that I work on it has been a collaboration for 25 years. It has existed, and people have been planning how we're going to do this experiment for longer than, say, Amazon and Google have existed. So this big data thing happened while we were building our experiment. We'd like to take advantage of it, but we can't be faulted for not having known about it. So now when we're trying to combine these two worlds, the obstacles are not just accidental. It's not just artifacts of technology choice, such as C++ in the particle physics world and Java in the Hadoop Spark world, which are rather hard to fit together, but that's just an accident. There are also essential qualities that the current big data systems don't offer. This is something that I've found through these investigations. However, it's not, I'm not going to cast it in a negative light. This is definitely a very positive thing, because it's an opportunity on both sides of the divide. There's like 2 alien civilizations that evolved in different planets. We have a lot to learn from each other. We have different kinds of problems, mostly, and we, in isolation, developed different solutions, and we can see what crosses, what we can both use. So then, the question, what is unique about the particle physics data? I've just said that it's not the size, because hundreds of petabytes are not unheard of. I'm going to argue that it's the object complexity. So for instance, this picture would represent 1 row in our data table. Right, all that stuff that's going on in there, those are all columns in some sort of table, and definitely put quotes around that, because our data are not stored in database tables. They're stored in files. And this has some downsides. naturally. We don't benefit from indexing, query planning, high-level query languages, all those things that in some fields are second nature. Every data pull is a custom C++ program written by the data analysts themselves, accessing lists of files, taking months while the user, the data analyst, chases down failures and stragglers. But even let's just say that we took all that data and we did put it into some kind of database systems, some relational or NoSQL, whatever, the things that are on the market now. I've been looking at this. I'm realizing the first thing that we'd do if we had all of our data in this is we'd have to pull it out again, because it just doesn't fit. It's not the right shape, so to speak. Why is that? Well, our data has a unusually complex structure. It's deeply nested and cross-linked. Now, the nesting nowadays is not such a problem. Drill, Parquet, and Arrow are big data projects that not only can handle nested data, but can explode them into columns for fast, sparse access, like we need. You might want only just a couple columns. You want to be able to read just those columns and not the whole thing. We can do, the big data world can do that with hierarchical data now. We've been doing it for longer, but that's OK. Well, because we needed it, actually. I should say that was driven by need. Also, we have cross-links or pointers. Now, you could support this with a graph database. It wouldn't be exactly how graph databases are usually used, and I think that this is even less of a driver of difference. Here's where the difference really is. The operations that we perform make intensive use of that structure in ways that would be really hard to use traditional databases for. So we frequently need to search through sublists, under constraints, optimizing pairing, iterating over combinatorics, all within one row of the data table. Even the simplest particle physics search criteria, if you were to put the data into a traditional database, would require all sorts of explodes and tags and joins in SQL, and I'll show that. To give a sense of the problem, I'll walk through the steps in analysis. So we start at the beginning. We build this detector. Looks like that. It's got all these channels. And then you put a particle collision in the middle of it, and you get pictures like the one on the right. The particles collide in the center, and then a whole bunch of new particles come out, and the new particles go through the layers of the detector, activating them at various points, and then you read it all out in wires to make this plot. So can you see where the particles went here? Like show of hands if you do. And OK, some hands. How about now? Make it a little easier to see. OK, so the first thing we do is we draw lines through them. We have software to find them and then fit them. And there can, of course, be more than one. And they can get fairly complex. So the raw data could have been described as a sparsely filled table. Like each one of those points, I can't walk over there. Each one of those points is on where it could have been off. And more than that, there's some position measurement involved in that too. But really, you could take each one of those millions of channels that come out and make each one of those millions of channels a separate column in some database, and there would just be a number associated with it, and most of them would be blank. But the reconstructed data, where those how many tracks you have, where they go, that's an arbitrary length list, which doesn't fit the table model very well at all. More than that, tracks are not the end. From tracks to particles, let me just explain what this picture is that you're seeing. On the left is where the collision actually happened. And you see a whole bunch of particles coming out of that. And those are measured tracks. And then, oh, I have a mouse, good. And then offset from that, you see some other particles coming out of here. And that's because one of the particles that started in the collision walked over here and then decayed into these things, some 3 millimeters away. And this sort of thing is the majority of what we're interested in. We're, for the most part, not interested in all of those really, really long-lived particles that live for like nanoseconds and make tracks through our detector. We're interested in the short-lived ones that decay 3 millimeters away, and usually we're interested in the ones that decay microns away. You know, you wouldn't even see them offset. So tracks have a structured association with each other. And those associations are not certain. We have to carry the flexibility through to the final analysis. There are a lot of them, too. This is a typical picture. When you run two beams through each other, you can get tens of collisions, and then they all spray out lots of stuff, and you have to undo all of that. So let's walk through an analysis, starting from the tracks, and see how the operations are complex. So suppose there's a particle called the Higgs that'll decay into two Z bosons, and each of those decays into 2 electrons or 2 muons. So you got this kind of an equation. So you've got to look at all those tracks, and you've got to figure out which ones are the electrons and which ones are the muons, and which are everything else. So you've got all these different kinds of subdetectors that measure different aspects of those tracks, and that's all collected into that picture. And you can use that information against each other to figure out which ones are the muons, which ones are the electrons. And then when you've identified them, you group them and compute the mass of the progenitor that would have decayed to those electrons or those 2 muons, or all 4 of them. And then you can plot that quantity. And if there is such a particle, the mass values that you compute will pile up at some value. And then all of the misidentifications that you made pile up elsewhere. So this is a typical analysis, and this is a very simple, clean analysis. It gets worse from here. Now, having our data as these objects, where there's an arbitrary length list of them, is much easier to do that than with a flat table. Like in this example here, to make a flat table, you have to say that you're only interested in 2 of them, and if there aren't 2, you have to put in NAs, and if there are 3, then you lost 1. It's just much easier to write algorithms over objects. Modern SQL can represent this kind of data. So here's how you might create a table with this kind of structure. But then if you wanted to do that Higgs search, which I claim is easy, you have to do a whole lot of work. And I would argue that this is in no way easier than just writing a nested for loop. As the data analyst, we'd really rather write that nested for loop, because this is crazy. So I started developing a language to try to help this. You don't have to throw the SQL type idea, the query language idea out, but you just need to extend it more so that we can do more with it. You can add first-class functions to something like SQL. So last year I started developing a language that would do this. And it was a declarative query language with a functional object-oriented syntax. This is what the Higgs analysis would look like in it. You can take the tracks in your event and .filter, say we want to filter on, and then you can take distinct pairs and .filter those pairs, and compute masses on them. This is the kind of thing that you'd want to be able to do. And this, coming from on the one side, the C++ world, this looks very oddly sleek. And then coming from the SQL world, this is looking oddly program-like. So it's somewhere in the middle to try to do both. Now, this language is great. Developing it has opened up a lot of ideas, and I won't be talking about it for the rest of this talk because, well, first of all, why is it great? By shrink wrapping the language on a problem, we have some nice features. We can automatically vectorize some calculations across objects. That was nice. We can do some 100% compile time error checking. This is when it's very SQL-like. We can do these things. But when I started this, I didn't see any other projects in this direction, and that's why I was developing my own. But now, in the past year, I'm starting to see these things popping up. So in SparkSQL 3.0, they're introducing a transform keyword that will allow you to put in, that's a functor for SQL. So it's coming from a SQL syntax, but it's this kind of idea. Also, Michael in US Regions AB after this talk, I recommend you go over there and see his talk on data fun, which is exactly this. It's a query language with where you can put in functions. Meanwhile, we discovered that Femtocode's internal data representation, which was sort of part of this whole big complex project, was orders of magnitude faster than scanning with our current methods. So we're realizing, oh, this is the key issue. It's not about making a new language. It's about data representation. And so maybe we should be barking up this tree right now. We should apply the new data representation on its own without introducing a new language and see what that gets us. So let me show you those orders of magnitude. Let's say that you want to do something kind of simple. You want to loop over the events. And inside of that, you want to loop over the tracks. And for each track, you want to fill a histogram. If you were to do it simply, if you were to do it the most straightforward way, you have some flattened track momentum array, and you just write a minimal loop over it, you can do that in 250 megahertz, with the 03 flag on, obviously. And with our current framework in the same units, 0.018. It's enormous, the difference. And is that just a mistake? Well, no. If you slowly add in the various things that our framework is doing, you can account for all those orders of magnitude. It's all there. To be fair, it's because our framework was not designed to do that. Our framework was not designed to run over all of the petabytes of data and make one plot. It was designed to extract a subset of events and a subset of attributes for the physicist to analyze locally. And locally can mean a bunch of different things. So one would never use the current framework to do this because it's too slow, but then it's slow because no users have asked for being able to do this. So the current jobs to select these subsets and bring them down can take weeks or months. And one analyst said 1.5 years was his data collection phase, and then he did his analysis afterward. The data analyst has to manage sets of files and chase down failed jobs, which is part of what adds to the time. Repeating the process is so time-consuming that analysis groups hedge their bets by requesting more data than they're sure that they'll need, because you don't want to be stuck in a situation where your local subset doesn't have something, and then you have to do this all again. So the process is slower and the download takes longer. Go to 1, right? This is like an optimization point. So really, we're talking about a change in behavior between one optimization point, which is big download, work locally, and another optimization point, which is small operations on a shared resource. So for this new style of analysis workflow to compete, and new to us, the responses have to be rapid enough for end-user analysis. They have to be able to make their plot, make a decision, make another plot, make a decision. And the interface has to allow for algorithms on nested objects. And this is why we can't just use an existing tool, because they don't do that. And if I'm wrong, tell me afterward. So now, we're trying to develop this kind of a system, or find such a system. And what was the key idea, the sort of the takeaway from the 4 orders of magnitude thing, was to leave the data in columns. I know this is a common thing to do in databases, but it's just not usually done with objects. So leaving the data in columns. Now, we've been like I said earlier, we've been storing data as exploded columns since the 90s because it was necessary in order to have this sparse read. And we've been doing this in a method that's similar but different from Apache Parquet because, of course, we're aliens. We've never spoken to them. But we also, one thing that we should be, that would be new is we also shouldn't be spending time materializing them as objects. So to show what that looks like, suppose that you have data like this. So there's a list of lists. Now, a way to store this kind of hierarchically nested data as columns, you could do it like this. And let's focus on this for a little bit because this is understanding how this works is kind of key. You take the data and you just put it all in one array, flattened across. And that array is what you're going to be able to run over very quickly by vectorizing calculations on it. Then you've just thrown away the nested list structure. To keep the nested lists, you have to make offset arrays, or alternatively, counts of how big each list and sublist is. Yeah, so these are offsets, and they are cumulative sums of what the counts would be. So you can just stare at that and see, works for a couple examples. Now, the user wants to be able to write something like this. This is absolutely the most natural way to walk over this if you're going to be computing some Higgs mass or something. Now, here's the thing. We shouldn't create the lists and sublists because that's a performance hit. Instead, we should take that code. Instead of bringing the data to where the code is, we should take the code to where the data is. We take that code and instead execute array lookups that look up the values in the arrays. So in a sense, we sort of partially compiled this against where we know that the data is actually located. And in fact, for this particular example, because it's a for loop of a for loop and you completely exhaust them, you could just do a single loop over the inner stuff. And you know how to do that by nesting these offset arrays. Now, that data representation is not anything new. The data representation is how Apache Arrow does it. And the code transformation can be automated. So let me show you some measurements in a real system. I'm using Python as a stepping stone toward Femtocode. By transforming Python object references, we can turn it into nothing but arrays for number crunching. And then we can take Numba, which is a Python to LLVM compiler, which only knows about arrays and numbers, and is only particularly good at optimizing code like that. But now we've given it code that's all just arrays and numbers, and it can go to town. So we'll give it something which is actually computing a mass. It's a function, for loop, and we're computing a mass. And notice here that the first one is a loop over all muons, and the inner one is a loop over not the same muon. So we're doing distinct pairs, which is something the physicists would naturally want to do. Then we translate this into array references. We pass it to some function that will first do the code transformation, Python ast to Python ast, and then give that Python ast to Numba and let it actually compile it. And now we have astronomical speed-ups for this Python code relative to C++ code in our current framework. C++ code is down here at just a little bit more than a megahertz, and then this Python code is up at tens of megahertz. In fact, these are 4 different algorithms. The mass of pairs is the slowest algorithm. And if you dig into why is it slow, it's because we're computing cosine and cosh. We're actually at the level where that matters. We've never been at the level where that matters. So we'll start putting in lookup tables for trig functions. Yeah, that's great. Couldn't be happier. So general code transformation is hard. for all types of data, it would be an enormous project. So let's instead focus on a minimal set of type generators. Let's first sit back and think, what is the least you can get away with? And this is what I came up with. Primitives, you need fixed with numbers, Booleans, characters. You need arbitrary length lists of another type, and this is the hard part, the lists. Unions and records. You know what records are? They're structures, they're the product types. The unions are the sum types. And actually, for the particle physics data, they don't really even need the unions. I just wanted to have it be a complete type system. If you have product types, you really ought to have sum types. Other common types, strings and such, you can construct them from these. So the code transformation only really needs to know about these basic kinds of types. And anything else that you do on top of that, well, it's after the code transformation. I have a project where GitHub repository where we're doing these code transformations, and I would like people to look at it if they're interested and get together on that. Relationship of this to Apache Arrow. The way that the primitives, lists, sparse unions, and records were expressed is a subset of the Arrow specification. So we're doing it the same way that Arrow does it. So in principle, you ought to be able to take some Python code with arbitrary nested loops and function calls, if you compile those also, and make them run fast on Arrow data frames. And that can be very interesting to people who are using Spark and Pandas and Drill and Impala and HBase and all these other things that are supposed to start using Arrow in the near future. So currently, most of the uses of Arrow that I've seen have been for flat tables, where, yeah, you can do pandas operations, it's easy. If you want to do something complex on structured data, it can represent the structured data, but you can't write the code so it'll run fast. Well, this will help you write the code so it'll run fast. So is anyone interested in that? Oh, really? Oh, OK. Well, I want to talk to you. So last thought. Another thing that we should do about leaving the data in columns, we can also manage the data in columns. So one of the reasons that users copy data is to enrich it with derived features. So here, let's say that we've got a collection of lists of electrons. So first event, second event, third event, and then these are all the columns. You have an offset and then some data. And you want to add Z bosons to that because you do a search for Z bosons, and then the first event you decide that that this electron and this electron together make a Z boson. In the second event you say that these two do, and in the third event you say, oh, I have two Z bosons, this one and that one. You would like to be able to add that to the data set and make a new data set that has that. And it would even be nice to be able to keep the original data set around. You'd like to be able to have two versions of this data set share most of the underlying data. Currently, with files and such, we can't do that. You have to make a new file. But if we manage the data as columns, if they're addressed individually, if they're in some object store or something, then users can change the structure of the data by adding new columns without copying, and then we can just say that this larger set of columns is another data set, and the smaller set of columns is the original one. So, my last slide, conclusions. I hope it was interesting to learn about data issues in particle physics, but I'm really interested in hearing back from you, and maybe especially you. Do you have any suggestions, or do you think these suggestions for me, like stuff I haven't heard of, or do you think that these tools could be useful in your work, like we're doing these things and you'd like to benefit from them too? If you think it would help you, but it needs to be more mature, are you interested in collaborating? This is exactly what I want to do. This is why I came here, is because I want to, for one thing, get you excited about this, and then also see if we can work together. So, thank you.